too far into all of this, I thought I'd give kind of a little bit of a demonstration as to what makes MaxEnt so useful. And this is a very simple example, and I fear maybe even a little bit underwhelming, but I'll try to expand on the virtues of MaxEnt through this example. Okay, so say that we have some data, and right now we're going to use data that is discrete and non-negative, so we can have values from 0 to any arbitrary number, infinity, as long as it's an integer, 0, 1, 2, 3, 4, and so on. Okay, and we're going to stipulate right here that it's distributed as a geometric distribution, and that distribution is shown below. It's p times 1 minus p raised to the y minus 1 power, where p here is a parameter, right? It is the probability of a success. So you might use this kind of a distribution to model how many tails will you flip before you finally flip a heads, okay? Where the probability of heads would be p and tails would be 1 minus p. All right. So we're going to generate some data here. So we're going to generate 50 observations where the parameter p is a biased coin, so it's at 1/3. And so we're going to generate 50 observations from a geometric distribution that has parameter p, where p is, again, 1/3. And then we'll just look at what that data looks like. Okay, so this is the empirical distribution of our data. Okay, so each one of those bars represents some collection of y values, where again y is the number of tails we get before we get heads on this biased coin, so to speak. Okay. Now, say that we okay, so this is not that confusing, but sometimes it's hard to change mindsets here. So let's say that we just found the data that's represented in this histogram. Okay, so we didn't get to set the parameters. This is just what we found, and now we want to model this data, right? And so modeling the data means trying to find a good estimate for p here. For p here. All right. Now, when it turns out that when you have a named distribution like this, you can find there's very simple ways of finding p here, but one way that we might do it is to use R's base functions. And so here we could do it with the GLM function. If you're not familiar with any of this, that's absolutely okay. It has no bearing on where we're going in this particular video. But we could find an estimate for the parameter p by running this code here. And the thing to notice about this code is that these are basic commands that are in any software that you have, statistical software that you have, and it's very simple. It's here it's literally 2 lines of code. Okay, it's very, very easy. And the estimate that we got from executing that code right there was about 33%, right? 32.894 ... Well, that is almost exactly what we set the parameter to be. Okay, so that's good. That's reassuring, right? So we were able to successfully estimate the parameter and therefore model the distribution. That's great. Well, in MaxEnt, we take a different approach. We don't have these nice simple commands like GLM if you're working in R. Instead, we have to build some things, and we'll get into what has to be built and all of those things eventually. But that code is represented in these 2 blocks here and here. And again, I'm not going to walk through the code. That will come in time. But let me point out a couple things. So we're going to run this, and we get almost an identical estimate. It might be different once you get down into some of the later decimal points, but it is an almost identical estimate. And what's more is it is also almost identical to the actual value of I don't want to say of the data, the data was a sample of whatever, but we get something close to the set parameter value. Okay, so what do I want to point out here? I want to point out that we did this alternative way of trying to estimate the parameter and therefore the probability distribution of the data. And secondly, that it was more work. This, what we did here doing MaxEnt was more work. And so this is kind of the first thing to know about MaxEnt, which is if you know that there are non-MaxEnt methods for doing what you're going to do, then you should use those other methods, okay? Because they are less work. And for the most part, the other methods have been derived from MaxEnt. All right. Well, so that's all great. But let's say that our data up here, could not become infinite. It could not go all the way to infinity, right? Let's say that we knew because of some peculiarity of the data or the experiment or whatever it happens to be, that there was an upper limit to the data, right? Well, think about what this is going to do to the match between our estimate of the parameter p using the GLM function and what the actual distribution will have to do. The GLM function, whether you know this or not, when we tell it what kind of distribution we have, so we've told it, with that line right there, we've told it that we have a geometric distribution, and so it assumes that the data can, in theory, go all the way out to infinity. Okay, but now we're saying that no, there's actually a hard limit. It can't exceed some upper limit, whatever it happens to be. Well, now we don't have these nice simple tools like the GLM function or whatever we happen to use to accommodate this kind of weird thing, right? There's no closed form probability distribution that has values that go from 0 to say 12 or some hard upper limit. Well, now we need to find some other way of estimating our parameter, okay, and therefore the probability distribution. And it's in situations like this that MaxEnt shines, because with this same amount of work, or just maybe a little bit more, now MaxEnt can handle these weird restrictions on our data that cannot otherwise be handled by just this, the stock functions of your statistical software. And so the way that we'll do that is with this code block. Again, I'm not going to go through the code. There will be time to do that as we go forward. But I'm just going to run it, and I'm going to compare the probability distributions between, again, the stock R functions, its probability estimate, okay, with the MaxEnt estimate, where the MaxEnt estimate is the only one that can respect the fact that there is an upper bound. Okay, so here we have our plot. I'll blow it up for us. Okay, so the red is the bounded MaxEnt problem, and the blue is the ordinary geometric distribution using GLM. And you notice that they differ at each of the possible values, so that's one thing. But notice that if we resort to using just the GLM, it will assign values that are impossible, that go beyond the max. So, it's saying that a value of 11 has some probability. But if our data is bounded at 10, which is what the MaxEnt distribution here is respecting, then it will then the GLM version, or the stock version, will assign probabilities to impossible events, okay? And maybe that's an okay approximation, or maybe it's a disastrous approximation. We don't, it depends on the context of the problem. But this is really the power of MaxEnt, is that we can apply very bizarre restrictions to the data and come out with the appropriate probability distribution. Probability distributions that are not hard-coded into software. That's really the whole very cool and powerful and flexible thing about using MaxEnt. Okay.